Alrighty. Let's talk then about enthalpy. I'm going to build this up to get there. This is going to be based off of our internal energy discussions that we just finished. Um, but enthalpy is going to be kind of our important ending point for what we're going to deal with thermodynamics. Let's consider this reaction. This reaction here is what's used to set off car airbags. Okay. Um, And so there's a catalyst in there that gets triggered. When the catalyst is released, it instantly reacts with the sodium azide that releases a bunch of nitrogen gas, and nitrogen gas is what's inflating the balloon. Okay. We can consider two different um, conditions under which we could do this reaction. One of those is constant volume. And in constant volume, that just means we have a rigid container and that the volume isn't changing. What that does is it traps all the gas inside the original container. And so when the reaction goes off, um, all the gas is trapped inside. And so we have an increase in the pressure. Okay, we'll talk about pressure when we get to gases a little bit more too. The other way to do it is when we have constant pressure. Constant pressure. This means that we have a changeable volume. Okay, maybe it's an open container where the gas can escape, or maybe it's a balloon, like the airbag situation, or maybe it's like this idea here with a piston, right? The same thing happens in your car, right? Cars work off of pistons, car engines work off of pistons, and they work with the same scenario. Okay, we have our azide in here, we do the reaction, it releases gas, and the gas pushes the piston up. So this is doing work. Okay, so the difference here is that at constant pressure, we're doing work. At constant volume, we're not doing work. Okay, but the reaction is the same as we do it. Okay, um, so let's see what's happening here. We can come up with an equation for work based off of this scenario. We can say that the work involved is equal to um, pressure, right? Because we're at a constant pressure times whatever the change in the volume is. Since the system here is doing work on the surroundings, this work is negative because the system is giving its work away. Okay. Again, this equation would be given. Okay. You just need to know how to use it and what it means. Okay. Because the work is being done by the system. This is negative work. Okay. All right. When we think about the units of work, units of work are energy units. Okay, so typically we'll see this as joules. Maybe we'll see this as kilojoules when we're doing um, energy units. Okay, um, we'll typically deal with pressure in terms of a unit called atmospheres, and we'll get into pressure and talk about atmospheres when we get to the gas chapter next. Okay, um, since work is the pressure times the change in volume, our pressure is units of atmospheres, our volume is units of liters, and therefore we're going to have units of what we say liter atmospheres. And this is technically an energy unit, although it's a weird looking energy unit. Okay. We can convert liter atmospheres into joules. And we can do that by saying that 1 liter atmosphere is equal to 101.33 joules. This is not exact, so this is 5 sig figs. And this will be given, well, not the number of sig figs, but the conversion factor will be given if we need it to do any work calculations with stuff. Okay. All right. Let's work an example then. Here we have a chemical reaction that's happening that's inflating a balloon. Okay. The balloon inflates, starts at 55 milliliters and inflates to 200 2.93 liters. It's working against an external pressure of 9.68 atmospheres, and we want to know how much work is done in units of joules. Okay, here's the conversion factor we're going to need. We need our equation. We'll be given this equation. Work equals minus the pressure times the change in the change in the volume. Okay. Unfortunately, we have two different volume units here. We have milliliters and we have liters. So we can't just subtract them. We have to convert the milliliters into liters because we need liters to do liter atmospheres. Okay. So we'll take a quick sidebar here and convert our milliliters into liters. This is 0.0550 liters. Okay, that looks weird. 0.55. Okay, now we have our thing. We probably also want to figure out delta V. You can do this in one step or two steps, depending on what you're feeling like in the moment. I'm just going to calculate delta V and then stick it in there because that way we can see all the steps. Remember, this is V final minus V initial. Anytime we have delta, it's always final minus initial. So this is 2.93 liters minus 0.0550 liters. Sorry, excuse me. So this is 2.875 liters with 2 decimal places on it. Okay. Once we have our delta V, we can figure out our pressure. Not our pressure, we can figure out our work because work is equal to minus P delta V. So we don't want to forget the minus. The pressure is the pressure, 968 atmospheres. And now we know our delta V, 2.875 liters. So this is negative, crap, come on, negative 2.83475 liter atmospheres. Okay, this has 3 significant figures right there. Okay, then we can go ahead and take a stab and say, let's convert this to joules, right? And we know that wish I could remember how my finger does, so it moves that thing around. I don't even know if you guys can see it, but it makes it all weird to me. Okay, 1 liter atmosphere is 101.33 joules. And so this ends up being negative 287.245 joules, which for 3 significant figures rounds to negative 287 joules. Okay, so that's the work that was done. And since it's negative, we've had the work was done by the system on the surroundings. Okay. If the surroundings were doing work on the system, then the volume change would have been opposite, and we would have ended up with 0.0550 minus 0.293, 2.93, and this would have given us negative delta V, which negative times negative would be a positive, and the positive would be the work done on the system. Okay. All right. Now, enthalpy. Let's get into enthalpy. If we're doing something at constant volume, remember constant volume, we said, right, we're doing a rigid container. We don't do any work. Everything is trapped inside the container. Ultimately, this will give us a value of delta U, and we'll talk about that in another video. Okay. At constant pressure, what we're thinking about is an open container, something that's movable piston so that the volume can change. Okay. In this case, we're still exchanging work with the surroundings. Okay, it's still happening. We have just made the decision that we don't care about the work that's there. Essentially, we are going to ignore work. Okay, you can think of it this way. If you're boiling a pot of water and you want to know how much heat it takes to boil the water, we don't care necessarily that water vapor is leaving the system and moving air particles out of the way. That's the change in volume. We have things going like that, right? If you're using a Bunsen burner, we don't care how the air around the Bunsen burner is moving. We just care about what the temperature of our reaction is, okay? So chemists have made up, or physicists, some scientist somewhere has made up this concept of enthalpy, okay? It's a man-made construct that deals with heat changes at constant pressure. And they've defined this. This is H. And what they've said is enthalpy is equal to internal energy plus the pressure times the volume. Okay. All of these things are state functions, and enthalpy itself. Why am I stuck here? Come on, go back. Okay. Enthalpy itself is a state function. Okay. Which means we can say that delta H is equal to delta U plus P times delta V. Okay. Remembering here that P was a constant, which is why we don't have delta P. Okay. We can also say that our work, no, not work, our delta U, there we go, is the heat plus the work. Okay. At constant pressure, right, then we can say this is Q delta P, blah, blah, blah. Where am I at? Then we can also say our work is minus P delta V. Okay. What do we notice here? We have P delta V over here, and we have P delta V over here, and we can sub those things in and say that our delta H is equal to delta U plus work, oops, right, P delta V, right, this is plus work, that's our enthalpy expression, minus work. No, oh my God, I should not do this when I'm tired, I'm sorry. Like, that doesn't make any sense, I'm just copying the same shit down. Okay, heat plus work, that's delta U, plus P delta V is equal to minus the work, so we sub that in there. Okay, if we take plus work and minus work, our work cancels out. So we can say our delta H is really just related to the heat at constant pressure. Okay, that's why we're doing this. This is ignoring the work and getting to do that. Okay. Essentially what's happening here is if we do this at constant volume, we're turning our work and manifesting the work as heat and measuring the total energy, or delta U. At constant pressure, we ignore the work and we measure enthalpy. This is only the heat. Okay. Enthalpy has the same sign convention that everything else does. Okay. Positive is into the system and negative is out of the system. Okay. We can also dub these things as endothermic and exothermic, right? Positive is into the system, that's endothermic, and negative is out of the system, so that's exothermic. Okay. All of those things still apply. Okay, just we're thinking at constant pressure so we can deal with enthalpy. All right. Mainly a lot of what we're concerned, well, we're concerned about enthalpy, but there's a special enthalpy called enthalpy of reaction. Okay, and this is how the heat changes during a chemical reaction. Okay, it's a change in enthalpy, so we can say delta H of reaction. Okay, this is an extensive property. Do you remember this? Extensive property just means it depends on the amount of stuff. Okay. And more important, not more importantly, but also importantly, this always refers to a balanced chemical equation. Okay, so whenever we're talking about delta H of reaction, it's related to a balanced chemical equation, which means we can tag in the delta H for a particular reaction. This is what we're making is called a thermochemical equation, okay? And in the thermochemical equation, delta H acts like a coefficient and relates to moles by the coefficients, okay? So we could make conversion factors that said, I don't know, that you'll get negative 2044 kilojoules, or you can say 244 kilojoules released for every 1 mole of propane, C3H8. Okay, you can make all those conversion factors involving the delta H as long as you're using coefficients as we do that. Okay, this is a thermochemical equation. Let's go back. Okay, so what this means is everything's related. So 1 mole of propane gives you 2044 kilojoules released, right? We can say, oh, for every 3 moles of CO2 that are released, we're going to also get 2044 kilojoules, right? We could also say, hey, if we had 2 moles of propane, C3H8, this will give us 4,088 kilojoules out. Okay. All right. Let's take a stab at an example here. Okay. We've got 13.2 kilograms of propane, and we're going to do a complete combustion, which means we're going to get CO2 and water. We're going to burn it with oxygen and do that, right? This is a fuel, so it's good for that. Okay. We know how much energy is involved in this reaction, and is heat going to be absorbed or is heat going to be released? We can actually answer the second question first because we see it right here. There's a negative sign. This means released the heat. Okay. Now the rest of this is just dimensional analysis. We already know how to do this. We just need to make sure that we notice that we know how to do this. Okay. So 13.2 kilograms of propane, C3H8. Okay. We gotta get this to grams so we can use our molar mass, which I didn't give us, but I would give you. 1 kilogram is 1,000 grams. Okay, our molar mass tells us that 44.11 grams of C3H8 is 1 mole of C3H8. Okay, now the only new thing we've got here is we're going to say this is not equals, dummy, times 1 mole of C3H8 is going to give us 2044 kilojoules. That's the new thing. Okay, we can multiply this out like dimensional analysis, and we can say this is 611,670.8 kilojoules. Okay, and we can round this, and we'll say this is 6.12 times 10 to the 5th kilojoules. Okay, we can either say this is negative in the front because our delta H was negative, or we can say this was released. Okay, both of those mean the same thing. I'm just going to tack a negative on the front here to do that. Okay, if you want to do that too, you could also probably tack a negative there and a negative there. The negative is not super crucial as long as we're noting that our answer has negative or it's released, because that's what this was telling us in the beginning. Okay. We can do things with thermochemical equations, and we will come back to this later on too in another video. But phase labels are going to matter. Notice the only thing that's changing here in this equation is the phase label, right? We went from water liquid to water gas. This reaction required us to do a phase change, and that phase change is positive 44 kilojoules. So the phase labels are going to make a difference. You can multiply or divide by a factor. Okay, here's our original propane equation. We can multiply the whole thing by 2, and if we do that, we multiply delta H by 2 and get 4,088 kilojoules out. Notice this isn't officially balanced the way we said it was going to be, but for thermochemical equations, we can do this and look at it and see that. We could also divide it, and now we can have fractions in here too. It looks weird, but it still works, right? If we divide the first equation by 2, right, then we get a half of propane, 5 halves of O2, 3 halves of CO2, 2 waters, and it cuts our heat out in half, right? 2044 becomes 1022, okay? We can also reverse the equation, right? If we take our initial equation with water and instead of evaporating it and going to a gas, we're going to condense it and go to a liquid. The number is the same number of kilojoules, but we're going in the other direction. Direction changes, so we're going to flip the sign. Okay. I think that's all I got for this one on enthalpy. Uh, Next time we'll talk about all the things we can do with enthalpy. We can talk about measuring enthalpy and how we do that. Um, and yep, I will talk at you later and let me know if you need anything.